Okay, welcome to the DDPS seminar today. Before we introduce today's speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions so that our speaker can talk without unnecessary interruption. If you have clarification questions, you are welcome to unmute yourself and ask those questions. Otherwise, please use your chat room to post your questions so that we can address them in Q&A session at the end. Second, no classified discussion is allowed here, so watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. All right, that's about it. Now let me introduce our speaker. It is an honor to host today's speaker, Priya Danti, who is a PhD student in computer science and public policy at Carnegie Mellon University and the U.S. Department of Energy Computational Science Graduate Fellow. She is also a co-founder and chair of Climate Change AI, an initiative to catalyze impactful work in climate change and machine learning. Her work lies at the intersection of machine learning, electric power systems, and climate change mitigation. Specifically, her research explores ways to incorporate domain knowledge, such as power system physics, into machine learning models. Today, Priya will present incorporating power system physics into deep learning via implicit layers, which is a very interesting topic. So please enjoy a wonderful talk. Now, without further ado, let me pass the baton to Priya.
All right, thanks, Youngsu, for the kind introduction and for the invitation today. So yeah, as Youngsu mentioned, today I'll be talking about some work basically trying to incorporate physics and hard constraints from the electric power system into deep learning methods using a tool called implicit layers. If you have any questions during the talk, as Youngsu mentioned, please feel free to unmute yourself and ask. I'll also be monitoring the chat during the talk, so feel free to just drop your questions in there and I'll get to them as we go. So it's probably no news to a lot of people that deep learning is often referred to as a black box. So these two representations on the slide are, for instance, very popular representations that are often discussed. So one of which is a literal black box where we have some inputs and we produce some outputs. And another one where maybe we open up the box a little bit and write down these little traffic light looking thingies that fundamentally still then map from inputs to outputs. And so during this talk, I want to propose a very specific view of deep learning that then will kind of frame the way in which I kind of introduce this topic of implicit layers. So deep learning fundamentally can be viewed as differentiable function composition. So the composition of different functions that can be through which we can take derivatives. So for example, kind of looking at this little traffic light diagram on the slide, you can think of each of these little traffic lights as a function. Each of these functions has some parameters associated with it. And overall, we want to try to adjust these parameters, usually using a procedure called backpropagation, to try to minimize some notion of error or loss. So the basic idea here is that every single component of this neural network, so every single function that we are composing together within this neural network, needs to be differentiable. That then kind of potentially gives a slightly different view of what a deep learning layer is. So often when we talk about deep learning layers, we talk about them in terms of, okay, it's some activation function, there's a ReLU in this layer, there's a sigmoid in this layer. But really a deep learning layer can be thought of as a function with certain kinds of attributes. So these attributes are, one, the ability to map from inputs to outputs. This is the forward procedure. The ability to compute gradients of the outputs of that layer or the loss of the overall network with respect to the inputs or function parameters, so some backwards procedure. And ideally, though this is not necessary, ideally these are not too expensive to compute so you can actually kind of plug them into a deep network at scale. And so in general, the basic idea is that rather than viewing a neural network architecture as, again, some kind of black box that we can't modify or something that we choose without principle, we can actually create and insert custom layers into neural networks that allow us to express functions or relationships that we think are actually rather important for the domain that we might be trying to work in. And so sort of one kind of custom layer that I'd like to put forth is sort of this general class of layers called implicit layers. So to talk about implicit layers, I'll first talk about something that is not an implicit layer, which is an kind of quote unquote explicit layer. So the idea is that we're often used to dealing with deep network layers that are characterized by some kind of explicit function, some function where we can directly write down a mapping between some inputs x and the layer outputs z. And in general, it's fairly easy to differentiate through these various kinds of layers, in particular because we have some very nice explicit function that we can find the derivative with respect to. But we can also create layers that are characterized by implicit functions. So an implicit function is a function where you don't necessarily have an explicit mapping between the inputs and the outputs, but where you have some relationship like that one on the slide that basically characterizes this relationship between inputs and outputs. And the basic idea is that if you take the derivative through this kind of the fixed point of this implicit function, or the equilibrium condition of this implicit function, and write out the chain rule and so forth, then you get some way, some kind of relationship that you can write out to actually get the derivative through this layer. So this is sort of a whirlwind overview of the kind of concept of implicit layers. And for those who are kind of interested in this, I would encourage you to check out the tutorial that's linked at the bottom left of the slide. But the basic idea here is that we can figure out a way to embed a relatively rich set of functions that can be represented by implicit layers into neural networks, because we can figure out how to take derivatives through these layers. And implicit layers have sort of taken many, many different forms in the literature. So for example, many of you have likely seen neural ordinary differential equations, or neural ODEs. But there have also been layers that encode, for example, rigid body physics, layers that basically encode infinite, quote unquote, infinite width sequence models, and also layers that encode optimization problems, in this case specifically convex optimization problems. So kind of this very small shift in the way we think about neural network layers can actually can kind of yield a very rich set of functions that we can actually embed into neural networks. So that's sort of the general idea of implicit layers. And I kind of want to show the power of these implicit layers, and the different kinds of things that you can use them to do in the context of my own work. And so I will sort of try to give an example of how you would build such an implicit layer for power system optimization, and then try to show basically how you would use this layer for different kinds of applications. So first, a little bit of background on power systems optimization. So an electric power system, basically the way in which, of course, you get electricity delivered to your house, for example. Managing an electric power system is actually a very complex endeavor. So specifically, you have some amount of electricity that's being produced on the electric grid at any given time from fossil fuel sources like coal and natural gas, but also from renewable energy like wind, solar, etc. And then you also have some amount of energy that is being consumed on the electric power grid at any moment. So both due to actual demand that we have, our lights, our heating and cooling systems, etc. And then also due to resistive losses that occur sort of as power is transmitted throughout the grid. And the kind of challenge with balancing electric power systems is that the amount of power supplied into the power grid has to equal the amount of power consumed at every single moment. And this can be really challenging when there's uncertainty in how much power is being consumed at any time. People's demand, for example, changes from moment to moment. And also how much power is being produced due to maybe changes in the weather, uncertainty in renewable, uncertainty in sort of cloud cover that might change the amount of solar power production, for example. And so The way that this kind of constraint of, electricity supply has to equal electricity demand is often kind of addressed in power systems is through the use of a optimization problem called AC optimal power flow, which is this problem on the slide. The basic idea of AC optimal power flow is that we want to minimize some objective on the power grid, usually the costs of power production. And I just want to point out that this sort of variable we're optimizing over, which contains many different quantities, many different power system quantities that we need to solve for, includes the amount of power that is produced at each power generator. But basically, the optimization objective here is to minimize the cost of power production. We want to do this subject to various linear constraints that occur on the power system, things even as simple as converting between different quantities. Various linear inequality constraints that encode things like limits on the outputs of various devices. So for example, a particular power generator might have a maximum or minimum amount of power that it can produce. And then finally, this last constraint, which is a power flow constraint, which basically enforces that the amount of power going into every node is equivalent to the amount of power coming out from every node. And this particular constraint is really nasty, it's non-convex, and as a result, this optimization problem overall is slow to solve. So there's a lot of work that tries to address how to solve this problem more quickly, for example. That's not necessarily the focus of this work, but generally this problem of AC optimal power flow, there's a lot of research on how to solve it more quickly. And then one additional thing I'll note is that the kind of amount of money you would pay for power, the power price at a given node is actually a dual variable on this power flow constraint. So if that means something to you, awesome. And if it doesn't, don't worry about it. Just something kind of interesting I wanted to point out. So how do we actually solve the AC optimal power flow problem? And how do we turn it into a neural network layer? So the basic idea for solving AC optimal power flow, a forward procedure, there are many different ways you could solve this problem, but I'm just going to pose one here. So first, in general, in a lot of these cases, we assume that the function of the cost of power production is basically a quadratic function of power production. And we also basically say, okay, this overall problem is actually kind of hard to solve because of this kind of non-linear power flow constraint. Let's linearize this constraint. So imagine that we have some current guess for the outputs of the optimization problem. Let's linearize it around that guess and then solve the problem. And the idea is that we can solve this via sequential quadratic programming. So basically, given this quadratic objective and this linearized constraint, we can solve this particular problem. We can come up with some new guess for the solution. We can relinearize our constraint around this new guess, and so on and so forth. We do this over and over again until the solution converges. Now, to actually incorporate ACOPF into a neural network, we have to differentiate through it. And the basic idea here is that the last quadratic program that we solve, this last convex quadratic program that we solve, is differentiable. And the way in which you differentiate through it is you write down something called the KKT conditions of this problem. So basically, the conditions written on the slide that characterize the optimal solutions of that particular problem. We can then, and I know this is a lot of ugly math on the slide, so the details aren't important here, but at a high level, we basically can implicitly differentiate through these KKT conditions, basically take the derivative through these various KKT conditions. And then as a result, basically write down this linear system that allows us to solve for these gradients, dz star, d theta, etc., that we actually need to solve for. So again, the sort of details on this particular slide aren't super important, but at a high level, we are basically taking this last quadratic program that we solved in order to solve ACOPF, to solve AC optimal power flow. We're writing down the optimality conditions of that particular optimization problem. And then we're taking derivatives through those optimality conditions. So before I move on to kind of specific applications that this kind of AC optimal power flow layer can be used for, are there any questions, either clarifying questions or anything else that anyone would like to ask first? Okay, so I will continue. So there are a number of different applications for which this kind of paradigm can be used. So the first is decision-driven forecasting. So specifically, one application in the context of electric power systems is demand forecasting. So as I mentioned before, electricity demand is really is potentially very variable, and this is really important to get a handle on in order to balance electric power systems. And so in general, we tend to want to predict future electricity demand, maybe with some notion of uncertainty, based on past electricity demand, as well as other factors such as weather and time. And we want to learn a neural network model, in this case, I'm going to call that H sub theta, that basically represents this relationship between our features and the predictions of future demand. And in general, what tends to be done is that the objective tends to be to try to create a neural network model that makes predictions of future demand that are as accurate as possible. So this could be represented by, for example, the equation on the slide, where for some inputs x, and some current estimate of our parameters theta, our estimated future demand is given by the output of our function on those inputs, so h sub theta of x. And then the true future demand is y. And this loss function would be something like the root mean squared error or other measure of accuracy of the predictions. So this is generally what we would do, basically try to optimize for the accuracy of the predictions. And I would argue that this is actually a kind of flawed notion. So in particular, accuracy doesn't always represent the thing that we want to optimize in order to improve the quality of decisions on the power grid. So to give an example there, if we, let's say, have a demand forecasting model that predicts X units of power consumption in the next 2 hours. Now, X units of power consumption in the next 2 hours is the actual correct answer. If we have one model that predicts that the power consumption will be X plus 10, and another model that predicts X minus 10, so one that over predicts by 10 and one that under predicts by 10, the accuracy of these two models would be the same. But these models actually would have very different implications for power system operation. So for example, if I overpredict electricity demand by 10 units, that might cause a power system operator to overprocure electricity. And some of that electricity would then need to be wasted, which would have bad implications for the cost of operation, but not necessarily be the worst thing in the world. That said, if one were to underpredict demand by 10 units, then an electricity system operator may then underprocure power and then need to scramble at the last minute to make up that power generation. So while from an accuracy perspective, an underprediction and an overprediction of 10 units may be similar, from an actual decision-making perspective, they're not. And so a question can then be, how do we actually incorporate knowledge about the decision-making procedure into our forecasting model in order to then make sure that our model isn't making fatal mistakes that are really very bad for the application? And so the way we can think about this is, instead of just thinking about, well, what are our inputs and what is our prediction of future demand, we can also think about, if I make a prediction of future demand, then what will the electricity generation schedule be that is made on the basis of that prediction? So in other words, if I make a prediction, what is the decision going to be that is made on the basis of my prediction? And then if I can understand basically how good that decision is, what the cost of that decision is, then I can basically encode that information into my model and train a model that is cognizant of the quality of the decision made on its basis. So instead of basically trying to optimize the accuracy of a given model, which is again the equation now on the bottom of the slide, we instead want to minimize the cost of the generation schedule that is made on the basis of our predictions when it acts upon actual electricity demand. So here, when we have x, again, our inputs. Theta is the parameters of our neural network model. And the idea is that we have a neural network model with some parameters. When it's given inputs, it will create some prediction. And we care about what is the decision, z star, that is made on the basis of our prediction. And then what we want to do is minimize the cost of that decision against the true power demand that we observe in the future. So that is basically this decision-driven forecasting paradigm. And so how does this tie into the idea of implicit layers? So the idea is that you would generally construct a neural network model to predict electricity demand, something like this generic neural network I have on the slide, where you have some inputs x, the output is y hat, so your prediction of demand, and then you have some parameters theta. The idea here, what we do here, is we actually, given the demand prediction y hat that comes out of our model, we run it through a power system optimization model, AC optimal power flow or economic dispatch or something else like that. And then we get some decision, z star, that is made on the basis of our prediction. And then we can compute the cost of that decision against the true power demand that we see and backpropagate this cost throughout the entire network, sort of update all of the parameters of the network on this basis. And then basically what this means is that the parameters of our demand forecasting network are being updated in a way that is cognizant of the overall system cost that we're actually trying to minimize. And the kind of upshot here is that this decision-driven approach, or this kind of approach, can in general dramatically reduce the cost of scheduling power on the electric grid. So to show that, first, I want to show the performance of two different models. So the kind of green solid line is our network, and the red dashed line is a network that is trying to optimize just for accuracy. The setting we're looking at is where at the beginning of the day, you're predicting electricity demand 24 hours out. And then the the x-axis is the hour of the day for which we're making the prediction. And the y-axis here is the root mean squared error of the prediction. So what this particular plot shows is that the kind of accuracy optimizing model, the model that we're comparing against, is actually more accurate, has a lower root mean squared error than our model. And that makes sense. It's optimizing for accuracy. On the other hand, when we look at performance not in terms of just the pure accuracy of the model, but when we look at basically how good a decision did it allow us to make, so here the y-axis is now the overall cost of scheduling the power system, what we see is that the cost associated with our model is actually much, much lower. So even though our model is less accurate, in some sense it is worse in terms of a standard metric like accuracy that we would usually use, it is actually better in terms of enabling power system operators to make decisions regarding how they should actually schedule power in a way that dramatically reduces costs. And in this case, in our simulated setting, the improvement in generator scheduling costs was actually around 40%.
Hi, Priya, can I interrupt to ask a question?
Yes, please.
So if I understand this correctly, looking at the figure on the right, over the first 8 hours, the task loss is essentially the same, but then is there some threshold over which the accuracy is, there's just a divergence right at about the 10-hour mark, which is surprising looking at the RMSE. So I'd be interesting to see is that a threshold effect where over a certain loss, your task loss blows up?
Yeah, that's a great question. So what is actually happening here is that there are constraints that basically, ramping constraints that basically determine, based on how much power I decided to produce from a particular generator in a particular hour, this is the amount of power I can produce in the next hour, which cannot be kind of too much more or too much less than what it was producing in the previous hour. So there's these various kinds of ramping constraints that occur. And so what I think is basically happening under the hood here is that initially, when the accuracy is good, there are many different things you can do in terms of actually, how you actually schedule power and so forth. But then those early decisions that you make kind of affect what later decisions you can make in terms of scheduling power. And basically around that 8-9 hour mark, that's basically where the kinds of mistakes that the root mean squared error model is making have basically caused the generator scheduling to go into a state where it's not able to sort of recover or compensate for various kinds of, I guess, like lack of look ahead that it had before. I don't know if that answers your question.
Yeah, that makes perfect sense. Thank you.
Okay. So Brenda asks, slide 18, which model is more transferable though? Did you try transferring this model to another time period and see which is more generalizable? So that's a great question. And I guess two comments on that basis. So this is actually over many different 24-hour periods. So what you're seeing is sort of an average over both many different data points and also many different replicates of the same experiment. But the general question I think still holds. If you're training a task-based model, will it really generalize to other settings? And the answer here is yes and no. So the reason you would train a task-based model is because you want it to perform very well on a particular task. That said, it's not necessarily a ton of effort to create a task-based model for a particular task. So in this experiment, what we actually did is we pre-trained our model with less data because we had some holdout data, but basically we pre-trained a accuracy optimizing model, a root mean squared error optimizing model, and then sort of took that model and trained it a few more steps in order to tune it towards the task loss. And so the idea is that we started with a base model that is in some sense kind of general, but we were able to optimize it fairly quickly for our particular task at hand.
I have one quick question. Maybe you already mentioned it, but can you just define task loss really quickly? Because RMSE is like kind of very clear to everyone, like it predicted something and that's the error. But what exactly is task loss like mathematically and then also practically?
Yeah, so task loss is this sort of, and thank you for, I didn't clarify that well. So it's this sort of optimization objective that I've written here, which is the kind of power or the kind of cost of creating this kind of electricity generation schedule when it acts upon a particular demand profile. And I haven't defined this on the slide here, but this depends on the particular task, of course. And so in this case, what it actually represents is there's a particular cost for basically oversupplying electricity compared to the actual amount of demand. And there's another cost for undersupplying electricity at any given moment with respect to the actual demand. And these have different weights on them. So the cost of oversupplying is in some sense less weighted than the cost of undersupplying, because of undersupplying is worse. And so this task loss is for kind of a, honestly, like kind of arbitrary setting of weights that we had created to just to heuristically give a sense of how bad or good these things are in relation to each other, but you would want to, in some sense, tune those various weights based on the actual realities of the system.
I see. So in another system where maybe the overproduction is has a different weight than the underproduction, like maybe it's not energy related, but I don't know, manufacturing food or something like that. then those weights would change, and so the task loss definition would also change, right?
Yep. And then
so I guess go ahead.
Oh, and then and then you would train your model on that definition of task loss as opposed to a different definition of task loss. So the idea is here that you really are trying to fit, or quote unquote overfit, to the particular domain you care about by actually incorporating that actual loss function in.
I see. Okay. And if you had a different definition of task loss, even for this same problem, that would kind of affect what these two curves look like. Is that correct?
Absolutely. And this is kind of true for any metric, right? Like accuracy, any loss function, really you're always optimizing your model for some metric. And if the metric shifts out from under you, then your model is going to perform differently. And so sort of one kind of thematic takeaway of this work is really understand what your metric is. Don't necessarily kind of go for the default metric of, for example, accuracy, if that's not actually what you care about in your system. And sort of understand that kind of no loss function is really truly agnostic in the way that we kind of think it is.
Right. Okay. But so for this definition of task loss, that's kind of the appropriate one for this energy problem.
Absolutely.
Okay. Got it. Thank you.
Yeah. No, thank you. That's a great question. Okay. So Jerome mentions, one of the issues that I wonder about is the requirement for differentiability. There are a lot of decisions, and those are usually the most important ones that involve discrete points. So turn on or buy a new generator that involve, huge discrete costs, etc. So Jerome, that's absolutely a great question. So in this case, we're definitely just looking at the AC optimal power flow settings. So kind of like instantaneous scheduling decisions. We're not looking at the kind of unit commitment setting. That said, there actually has been some amount of work, though not necessarily yet applied to power systems, that has tried to provide the ability to differentiate through combinatorial optimization problems or discrete optimization problems of different forms. And I think that would be really actually a quite important area of future work in the context of power systems if we really want to bring, for example, unit commitment decisions into deep learning models. Okay, and so Brenda asks, the formulation is deterministic. How are you addressing uncertainties? So that's a really great question here. So what we're doing is that when we kind of create the task loss, so the task loss, the actual task loss is an expectation of this kind of overproduction, underproduction cost over the actual demand that we see, but the demand is of course stochastic. And so what we actually do when we're running the deep network model is we make an assumption that the demand function is going to be normally distributed. And so we then kind of rewrite analytically that expectation in terms of the mean and standard deviation of the demand function, and our network predicts the mean and standard deviation. So there's actually, even though the kind of high level pitch has been, train your neural network on the actual task loss that will be happening in the real world. We did make an assumption, and during training, we did say, okay, we're actually going to make a Gaussian assumption here, even though during test time, that's not necessarily true. But even with that, basically it turns out that assumption of assuming that the future demand is Gaussian is a kind of less harmful assumption than sort of the accuracy one is kind of what the result is showing here, but we did have to find a way to do this analytically, basically.
Okay, Priya, we are getting many questions, but I maybe move on for now and then address that in Q&A.
Yeah, that sounds good to me.
We want to hear you more about what you prepared.
There we go. All right. Thanks, Young-Soo, and onwards I go. Thanks for everyone for the great questions. All right. So application 2 is addressing the vulnerability of power grid data. So in electric power systems, a lot of entities sort of face various challenges around whether they should make certain power system data private or public. So for instance, releasing information about electricity bids, how much different power generators or market players are bidding into an electricity market, may allow some players to exert market power to basically distort the outcomes of the market on the basis of that information. And releasing other information, stuff like the topology of the power grid, could lead to cybersecurity risks. On the other hand, there are actually lots of reasons that we want to make data public. So for instance, many power system operators publish power prices to promote market transparency, or the US Environmental Protection Agency publishes the power generation and emissions associated with large fossil fuel generators at every hour in order to facilitate emissions monitoring. So the idea is, yes, there's a lot of data that's public, and then there's a lot of data that's intentionally kept private. And a question is there potentially actually leakage between these two things? Is there not actually as big a separation between private and public data as we think there is? And so the question we ask in this piece of work is basically, can unknown or private information on the power grid be reverse engineered from information that is already available? So in the US context, we can think about things like generator power injections and locational power prices on the power grid as being available, and things like electricity bids and the structure of the power grid, or the admittance matrix, for those who are familiar with power systems terminology, as being unknown. And yet we do kind of know the relationship between these known and unknown quantities. At a high level, they are described by power system optimization decisions, which I will kind of simplify to being AC optimal power flow in this case. And so we can write down sort of an attempt to try to guess the unknown information from the known information as this problem of inverse optimal power flow. The basic idea is that if we have some guesses for the bidding parameters, so that's C hat, and for the power grid structure, that's Y hat, and we put those into an AC optimal power flow model along with information about power demands, then that AC optimal power flow model will give us an estimate of what the power generation and the locational prices would be if our estimates of these unknown parameters are correct. And then if we can basically figure out, well, what input parameters, what private parameters can I choose that actually lead the outputs of my ACOPF model to be close to the real values of power generation and power prices that I observe, then it is possible, though not necessarily guaranteed, but it is possible that I have basically guessed the values of these private parameters properly. And so with any optimization problem, for those who work in optimization, it's always really easy to write it down. It's often very hard to solve the problem. And so the way we solve this problem is actually through adjoint methods, or you can, again, think of this as sort of a differentiable layer that we use in order to solve this problem. So the basic idea is that we can kind of write our parameter identification model down like this, where we have some kind of AC optimal power flow, differentiable object layer, whatever you want to call it. It's not really in a deep network here, but some kind of differentiable AC optimal power flow object. You then have some parameters. Here are your kind of guesses of your bidding curve, bidding costs, and then also of the grid structure. And then you put those into the AC optimal power flow. You kind of get out a guess for power generation and power prices. You compute some cost. How close is that to the actual quantities I see on the grid? And then you update your guesses, the parameters of the AC optimal power flow layer via backpropagation. So we initially test this out on a very small and simulated test case, just sort of some initial investigation. So it's a 14 bus test case with around 200 data points that are simulated on this grid. And what we find at a high level is that with very small amounts of data, so the number of data points we actually use in different experiments are on the x-axis, we are actually able to recover the bidding parameters, the costs of different generators, with very few data points. So here we have each generator 1, 2, and 3, or 8, I guess, in a different plot. And then the y-axis has the squared error. And you can sort of see that the squared error of our estimate sort of drops to 0 with way fewer than 10 data points. On the other hand, guessing the power grid structure is harder. These plots are a little strange to read, but the y-axis of each of these plots is the squared error of a parameter estimate of a particular grid parameter. And the x-axis here is sort of the the error over our kind of the output of our ACOPF model. And so you can think of the kind of being left on the x-axis here means we're at the beginning of our algorithm, and being all the way right on this x-axis here means we sort of run our algorithm to convergence. And the basic idea is that you would want to end up at this 0, 0 point on the right. You want, when our algorithm has stopped, for our estimate of the parameter to be correct. And we find for grid structure that this is sometimes true and sometimes not. Sometimes we get to this nice 0, 0 point, like for this solid blue line, where we have a parameter that we were able to guess. But then sometimes we end up with this orange dashed line, which basically says we ended up with the wrong value for our particular parameter. And so the idea here is that guessing the grid structure is potentially harder, potentially because also there are some parameters that don't necessarily affect the outcome of the power system optimization that often. Okay, so one last application before I wrap it up and get to the questions is an application to provably robust power system control. So the basic idea here is that deep reinforcement learning has started to, become a very popular method, especially in kind of, it has found a lot of success in gaming domains like Atari, Dota, Go, all of these kinds of things. And the reason it's been so successful is that it can learn very expressive policies, very expressive controllers. And it generally does this by exploring some system, trying out various things, optimizing its behavior based on that. DeepRL is in some ways in opposition to the area of robust control, which also aims to construct controllers for various kinds of control systems, but generally tends to limit itself to very simple, usually linear policies about which it can prove guarantees. And in particular, these guarantees usually are stability guarantees. I want to stabilize my system sort of at all costs, even in the worst case scenario for that particular system. And so both of these methods and both of these ways of looking at things tend to leave kind of leave various desired attributes on the table. Deep reinforcement learning can't make any guarantees in general about performance. But when you're operating something like a power system where a critical mistake means a blackout, you can't have that. You need to have certain kinds of performance guarantees that are satisfied by your algorithm. At the same time, robust control methods, which can give you those performance guarantees, tend to be really simple. And so you leave a lot of kind of actual average case performance on the table. And so the goal of this particular project is to bridge the gap between those two things. And so at a high level, our approach is basically to try to find a stabilizing set of actions that can be taken at any moment. And so I'm just going to breeze through this here, but basically given some uncertainty model of our underlying system, and then a kind of Lyapunov function, you can think of it as kind of a potential function for your system that you can obtain via robust control. The idea is that we basically find some set of actions that is safe, and there are some equations on the slide that describe what that means, but basically a set of actions that decrease our Lyapunov function, our potential function, even in the worst case under a system model. And then the basic idea is that we say, imagine we have the output of some neural network that is proposing some action that we take on this particular system. Can we project that output onto this set of actions that we've derived that we know are safe? And then if we can do that, if we can take the output of our neural network, if we can project it onto a safe set of actions, and then train this whole thing end to end, then we can find a way basically to optimize for performance while also guaranteeing that the system will stay stable. And so to kind of put this back again into the neural network picture world, the setup looks something like this, where you have your state, you have, again, a neural network with some parameters. Your neural network is proposing some initial action that you might take onto the system. And then we project that action onto the safe set of actions, get our final action, which is kind of provably satisfying various kinds of safety conditions on the system. And then we figure out how good that action is and update the parameters of the model accordingly. And what we see is as follows. So in this plot, the y-axis shows the sort of time-integrated control cost of various methods. The x-axis shows different methods that we're testing out. So the first three methods here are non-robust methods, LQR, which is a control theory method, and a model-based planner and proximal policy optimization, both of which are reinforcement learning methods. So these are sort of non-robust methods that we're testing. The fourth method here is a robust control method, robust linear quadratic regulator, but a robust control method. And then the last two here are our methods, basically robust variants of the two reinforcement learning algorithms that are trained using our method of just sort of inserting this projection layer into the last layer. And we're testing out two scenarios here. So the blue bars show performance under sort of ordinary conditions. Basically, the underlying system is operating in a relatively normal scenario. And then the blue bar here, and then the orange bar here shows the performance of the system in an adversarial setting. So here we actually have designed a model predictive controller based adversary, but basically an adversary that tries to create the worst possible disturbance on the system for every single method. And what we see is that under ordinary operation, so looking at the blue bar, our methods outperform the kind of robust control method. That said, we don't necessarily outperform the main reinforcement learning method. So in some sense, the kind of non-robust methods that are optimized for average case performance tend to do better than us in this sort of average case scenario, which is not surprising. That said, if you look at this adversarial setting, the orange bars, all of the robust methods, including ours, stay stable, whereas the non-robust methods go unstable. So these actually breaks in the bars. These bars actually go much higher than the y-axis shows, and this is a log scale. But the basic idea is that all of the non-robust methods go unstable and our methods stay stable. So the idea is that by kind of inserting this kind of safe projection layer, this projection onto a safe set of actions into the loop of the neural network, we can get improved average case performance over robust control methods, while unlike non-robust methods actually remaining stable in the system. So that's actually all I have. So the sort of summary here is that implicit layers can be a really powerful tool for physical applications like energy systems applications. They can enable decision-driven models. For example, the demand forecasting model I showed that are well embedded into the systems in which they're actually used. They can help provide inductive bias, or basically give some kind of notion of the actual physics or relationships that are held in the underlying system. So for example, the inverse optimal power flow application I showed. And then they can also help enforce hard constraints. So for example, in this provably robust control method, where we were enforcing hard robustness constraints of the underlying system via deep learning. So with that, I'm happy to take any questions, and thanks so much.
Thank you so much for the great talk, Priya. It was really great. Let's go back to the question by Greg. And he asked, you probably have access to the chat room.
Yes.
He asked, for any definition of task loss, is the optimization that includes that task loss always better than the optimization that just accounts for accuracy?
Yeah, so that's a great question. So I guess what I'll say is, if you are able to make a perfect prediction, then it doesn't matter what loss you use. If you make a perfect prediction, you can make perfect decisions on the basis of that. Absent that, though, I would say that using a task loss is a way to, I guess, more directly optimize for the metric that you actually care about. There are various scenarios where if you are, for example, tuning the models differently, or you're not training one of them properly, et cetera, that you could, in theory, have an accuracy optimizing model that does worse, or sorry, an accuracy optimizing model that does better in a task-based setting than a task-based model. I mean, there are a lot of implementation details that go into it. But in theory, if you actually want to optimize the task loss, then actually optimizing for the task loss is more likely to kind of yield that kind of result.
Okay, any other questions? I have a questions about the the 14 bus test cases model you solved for the second topic of your talk.
Mhm.
It's relatively small problems, right? For realistic power systems, there will be more buses, I would imagine.
Mhm.
So it's natural to think about the scalability, I guess. Do you have any thought of addressing that issue?
Yeah, it's a good question. So the for these kinds of optimization layers, I guess there's sort of two things, which is that is the AC optimal power flow solver itself going to scale, and is the differentiation through the solver going to scale? So the question of is the AC optimal power flow solver going to scale is certainly, of course, one that is addressed in the literature. How do you create solvers that converge when you're solving for larger systems? That said, I mean, like there are existing solvers that can, solve for up to a few thousand buses. So we sort of can leverage existing innovations there and sort of plug in the state of the art solver that you would like to use there. In the backward pass, all you really need is the kind of the Jacobian of the kind of forward pass solving procedure. So basically you can kind of the backward pass does not get that much more expensive to compute even as the system gets larger, because you're fundamentally doing one linear solve and one kind of matrix inversion. And if you can exploit sparsity in the structure and all that, all the better. Um, so we haven't tested it out on larger systems yet, but I'm kind of optimistic that it will scale. The other kind of idea is that we did a 14 bus test system, but we only used 200 data points. And if you think about a real world system, you have 760 data points a year if you have hourly data. And so in some sense, I think the scale of the data that we tested on is in some sense similar to the scale of the system that we tested on. And I would sort of expect that at least the bidding results would scale up in at least this kind of simulated setting.
Very good. I think this is a comment rather than a question from Brenda. She thinks in general it's easier to optimize the task than the accuracy, that is analogous of discriminative versus generative. Do you want to make any comment on that? Yeah.
No, I mean, I think, yeah, again, like sort of it all comes down to what is your particular objective for the particular problem, and then what do you want to do. So similarly, yeah, lots of different choices that people make in the context of generative and discriminative that end up mirroring that choice in this case as well. Absolutely.
Okay, next question by Rob. When you use an implicit layer, do you enforce the implicit constraint strongly or weakly?
Yeah, it's a great question. So we enforce it strongly. The idea being that the kind of, in its purest form, the differentiation through the equilibrium conditions or fixed point equations of that problem only technically give you the correct derivatives if you are at the optimum of the problem. This is sort of, it relies on the implicit function theorem, which basically tells you about how you can take derivatives at equilibrium. That said, a lot of deep learning is about making, heuristic optimizations and approximations for various tasks. So there are certainly some folks who are looking at, for example, how do you actually compute a derivative that is reasonable, even in a scenario where you haven't solved the forward pass fully to convergence. Or even if you have kind of on the other side, even if you have fully solved the forward pass to convergence, if the derivative is for some reason difficult or expensive to compute, for example, we were talking about discrete problems earlier, can you use an approximation of the derivative in the backward pass and still have that give you reasonable results? So definitely there's sort of a lot of work being done in this kind of, how do you get this to still work when you can't get both sides of this to hold exactly?
Very nice. Okay, any other questions?
I have a question. Can I just say it? Because I was
Yeah.
Okay. Thanks so much. Essentially your talk has touched upon convex optimization as well as, the differentiability, because I mean that's how we have to get the gradients to do the backprop. But have you thought about so I feel like differentiability is probably more important in that otherwise you cannot backprop through things. But have you guys thought about how do you apply that to non-convex optimization? type of problems. So something that I'm kind of curious about. Thanks.
Yeah, no, it's a great question. So, honestly, we haven't necessarily thought about this completely generally, but in like a slightly ad hoc manner. So, for example, this AC optimal power flow problem I was talking about is non-convex. We definitely sort of figured out a way to relax it, iteratively solve it, and figure out a way in which we could use a kind of convex final iterate and differentiate through that instead. But that was sort of our way of creating a differentiable version of this non-convex optimization problem. There's also been some work in like areas called like deep declarative networks that use a kind of differentiation through the Lagrangian in a way that I think theoretically can accommodate non-convex problems, but I can't recall whether they actually tried this out. And then one thing to try would also be if you have a solver and you are kind of if you have kind of a non-convex optimization solver that is iterative and you sort of solve it and you're solving some kinds of fixed point equations to find the final iterate, you can differentiate through those final fixed point equations. Now, the challenge is with all of these things, you often don't have guarantees about, for example, have I reached an optimum in a non-convex solver? And so you're going to tend to suffer from the same issues when then trying to come up with a differentiable layer for that. But definitely there are sort of ways to do it that I think have to be sort of adapted to the context of the individual non-convex problem. Yeah, but it's a great question and I think a really difficult one.
Okay, very nice. Any other question?
Hey Priya, I have a quick non-technical question. Are you guys
Sure.
doing another climate AI workshop at NeurIPS this year?
That's a great question. Thanks for asking it, Gavin. So yeah, we are hoping to hold a couple of different climate change AI workshops this upcoming year. Where for those who aren't as familiar with this venue, basically a venue to sort of meet other people and submit and share work at the intersection of climate change and machine learning. With all of these workshops, there's always an application process to after which the workshop organizer or the conference organizers need to select the workshop. But we are definitely hoping to hold a couple of workshops at the upcoming major conferences. So the best way to find out about that is to sign up for the Climate Change AI newsletter, which you can find on the Climate Change AI website. I can also drop the link into the chat. Yeah, so thanks for asking that.
Great. Yeah, good luck.
Thanks.
Wonderful. Any other questions? Well, I mean, we have 1 minute, but Priya, if you can, maybe advertise, your, nonprofit company, the climate change AI, within like 1 or 2 minutes, that would be awesome as a closing remark.
Absolutely. Yeah. So thank you for asking. So Climate Change AI is basically a volunteer initiative to try to catalyze impactful work at the intersection of climate change and machine learning. And so basically we tend to hold kind of workshops and other events to help people meet others who are working, for example, in machine learning or climate relevant areas. We also have some educational resources on our website, kind of recordings of past workshops. And digital resources such as a monthly newsletter and an online discussion forum. And we also have a kind of an ongoing call for a grants program on climate change and machine learning focused in sub-Saharan Africa. And we'll be also making similar, hopefully exciting announcements going forward regarding additional infrastructure and potentially funding programs. So definitely, if you're somebody who is working in this area of climate change and machine learning and or would like to kind of and would like to meet other people who are working in this area, I definitely encourage you to check out our website, resources, and various kinds of events. We also have a kind of every other week a virtual happy hour, kind of details on our website. So that's also something that if you're interested in sort of meeting others in this community in the short term, that you should feel free to check out.
Wonderful, wonderful. I mean, you are doing wonderful research and also as well as wonderful work for the climate change. That's awesome. Well, is there any other questions? If not, let's thank Priya for a wonderful talk and her participants today. Big applause.
Thank you so much for having me. It was fun.
All right.
And thanks
awesome.
everyone for the great questions.
Awesome. I hope you will get connected with some folks at Lawrence Livermore and continue the collaborations. That would
Absolutely.
be awesome. Okay, thank you so much. With that, we will adjourn the meeting today. Thank you so much for everyone joining us.